How's it going, guys? My name's Ashton, and today we're going to be looking at homework question number 2, sketching molar/mass fluxes and molar/mass diffusive fluxes. And I know what you're thinking, Ashton, where's the small whiteboard? Where's the whiteboard of worship? Unfortunately, that's not the case for today. You can't work it into this video, but that's alright. Anyways, I'm going to post the question up here, so if you guys want to take a second, pause, write down all your knowns and everything like that, and now let's get into it. So first what I did was I drew a picture. So we know that we have a capillary tube and that it's 10 centimeters long, and half of it, so 5 centimeters, is filled with H2O, while the other half, the right side I'm calling it, is filled with D2O. And let's write down our knowns. So our density of water is going to be 1,000 kilograms per meter cubed with a molecular weight of 18 grams per mole. We know through the question itself, it gives us that the density of D2O is 1,110 kilograms per meter cubed with a molecular weight of 20 grams per mole, respectively. And we know that the max molar diffusive flux at T equals 0.1 is 2.78 moles per meter cubed per second. So let's get into the nitty-gritty of it. Alright, so number 1 asks us to find the overall mass flux, and we know that the overall mass flux, which we represent by little n, is equal to the total mass concentration multiplied by our total velocity. And then you might be thinking, wow, we don't know any of those things. Well, we're going to solve for them both, so hang tight. So first, let's solve for our total mass concentration, which we know is equivalent to our mass concentration of H2O plus our mass concentration of D2O. And we also know that our mass concentration of some component, let's call it, say, component I, for example, is equal to our mass of that component over our total volume. So we can also simplify this further since we know two things. We know its molecular weight and we know its density. And we also know, since we know that our mass of some component is equal to its density times its volume, we can substitute that in since we know its density, and we can do something with the volume here in a second. I'll show you. So we have that our mass concentration of some component equals our density of the said component multiplied by the volume over our total volume. Now let's look at H2O first. So we know that the mass concentration of H2O is going to be our density of H2O, which is 1,000 kilograms per meter cubed, times 1/2 V total, since we know that water occupies half of the capillary tube, which is going to be half of the volume. We can actually cancel out our volumes here, which is going to be equal to our 1,000 times 1/2, which is going to be 500 kilograms per meter cubed. Next, we can find the mass concentration of the D2O component, which we know that the density from the given equation, or from the givens in our problem, is 1,110. Multiply that with the half the total volume, divided by the total volume. Our total volumes cancel out, leaving us with 1,110 times 1/2, which is going to be equal to 555 kilograms per meter cubed. Adding both of those together to get our total mass concentration, we get 1,055 kilograms per meter cubed. Now, looking at our total molar diffusive flux, we know that's equal to our molar diffusive flux of H2O plus our molar diffusive flux of D2O. And so we know that the maximum molar diffusive flux is going to be 2.78. We know that the molar diffusive flux of D2O is going to be negative 2.78. So we know the combined is going to be 0. The total will be 0. And then looking at, now let's solve for our velocity of our component. Since we know that the total is going to be 0, we can say that our molar diffusive flux of H2O is equal to our molar concentration of H2O times our velocity of H2O. And then to calculate our molar concentration of H2O, we can take our mass diffusive, or no, I'm sorry, not our mass diffusive, but our mass concentration of H2O divided by our molecular weight, which we know of water to be 18 grams per mole. We have to convert that to kilograms since we know that our mass concentration is in kilograms to be 27,777.77. Using the same process for our D2O, we get the 555 mass concentration that we calculated right here over our 20 grams per mole over 1,000 to convert it to kilograms per mole to get 27,750 for our molar concentration of D2O. Plugging these into our equation we have from earlier and solving for velocity through rearrangement, we get the velocity of H2O equals our molar diffusive flux of H2O over our molar concentration of H2O, which we know that it's 2.78 for our molar diffusive flux over our 27,777.77 molar concentration, which is going to give us a velocity of 1.008 times 10 to the negative fourth. Doing the same process again for D2O, substituting in the corresponding values, the negative 2.78 for molar diffusive flux, and then the 27,750 for the molar concentration of D2O, we get that the velocity, which is going to be in the opposite direction of our water, is going to be negative 1.0018 times 10 to the negative fourth meters per second. Looking at our total velocity, we know that it is going to be equal to our mass fraction of I'm sorry, I lost my train of thought. It's our mass fraction of H2O multiplied by our velocity of H2O plus our mass fraction of D2O multiplied by our velocity of D2O. And we know that our mass fraction of some component is going to be our mass concentration of said component over our total mass concentration. Plugging those into their respective places, we get that for our water, we get our 500, which we calculated right up here for our mass concentration. 500 over our total concentration, the 1,055, multiplied by our velocity of H2O plus our 5555 over our 1055 from our D2O multiplied by our velocity of D2O is going to give us a total velocity of negative 5.27 times 10 to the negative 6 meters per second. With our velocity solved for and our total mass concentration solved for, we can find our mass flux. So our total mass flux is going to be, a reminder, is equal to our mass concentration total multiplied by our total velocity, which is going to be our 1,055 multiplied by our total velocity of negative 5.27 times 10 to the negative 6, giving us a mass flux of negative 5.56 times 10 to the negative third kilograms per meter squared per second. Going to number 2, which our objective in number 2 is to find the order of magnitude for the maximum driving force for diffusion at t equals 0.1 seconds. Now we know from our book that the total our molar diffusive flux of all our components is going to be equal to 0. Therefore, our molar diffusive flux of component 1 plus our molar diffusive flux of component 2 is going to be 0. So this just means that our molar diffusive flux of component 2 is equal to our negative molar diffusive flux of component 1. We can say the same thing about our molar concentration of all our components. Their sum is going to be equal to 1, so we know that the molar concentration of component 1 plus the molar concentration of component 2 is going to be equal to 1. Therefore, our molar concentration of component 2 equals 1 minus the molar concentration of component 1. Now, solving for the driving force in of diffusion at t equals 1 seconds, we know that our d1 is going to be equal to our right Riemann sum of x, so the molar concentration of component I times the molar diffusion flux of component J minus our molar concentration of component J times our molar diffusion flux of component I, all over our total concentration multiplied by our Stefan-Maxwell constant from I to J. Subbing that out through our summation, we get that the molar concentration of component 1 multiplied by the molar diffusion flux of 1 minus the molar concentration of component 1 times the molar concentration of molar diffusion flux, which these is just going to equal 0, so we know this goes to 0, plus our molar concentration of component 1 times our molar diffusion flux component 2 minus our molar concentration of component 2 multiplied by our molar diffusion flux component 1 all over our total concentration and our Stefan-Maxwell constant for 1 to 2. And then since we know our Stefan-Maxwell constant of a liquid is going to be 10 to the negative 9th, we have that solved for. And we also know that the molar concentration for water is going to be 55,555, meaning all we have to do left over after we do our substitutions of these in, we get a final equation of negative molar diffusion flux component 1 over our total concentration divided by, or over our total concentration multiplied by our Stefan-Maxwell constant. So where we get our 55,555 times our 10 to the negative 9th, and then do our negative, don't forget the negative sign, 2.78 to give us negative 50,040.5, which also equals negative 5.004 times 10 to the 4, which that means our order of magnitude for D1 is going to be 10 to the 4th. Finally, let's look at our graphs from question part 3. Our first graph here is going to be our mass concentration graph. So on the left, we're going to have our H2O, and on the right, we're going to have our D2O, since they're separated by that barrier initially, and at 5 centimeters. So, because our x component is centimeters. So we're going to have all water initially on the left side, and on the right side, we're going to have all D2O. Next, we're going to look at the intermediate when they start to mix. So as we see, as we get closer and closer to the other side, we see that our mass concentration starts to decline to 0 at the other side because they're still mixing. And then finally, we have our, when they're completely mixed, and from our calculations earlier, we have our 500 for water and our 5 for our D2O, which we calculated right up here. Next, when we look at our molar concentration, we know they're still at 555 initially for both sides, and they're both the same. Then, as our intermediate, they start to intermix. They start to get mixed around because they're diffusing into each other. And then finally, they level out once the time reaches like infinity and they've reached equilibrium. They'll be back at their original spots. Our third graph is going to be our molar diffusive flux, which we know that at the opposite ends of the capillary tube, there's going to have nothing going on, so we have no diffusion over here. But then the closer we get to the center, initially, we get our spike to our maximum, which at t equals 0.1 seconds, of going to be 2.78 and negative 2.78 respectively. As time goes on, that gap where they interact, because they're diffusing together, widens. And then finally, at equilibrium, they're both just all mixed up together. And then looking at finally our last graph, which is going to be our total mass diffusive flux, which is going to be similar to our molar diffusive flux, but in the in the case where we're just going to have a steeper initially because they haven't diffused completely, followed by an intermediate when they're more diffused, so it's more of a gradual slope down to our number. And then finally when they're equilibrium, it's just a straight line because they've been completely diffused and everything like that. Now, I hope you guys learned something today and that you enjoyed the video, and thank you for watching.